Greetings and welcome, or welcome back as the case may be. Today's Monday, so that generally means a science-based topic. So today's post is going to be about optical telescopes, how they work, and things like that. The basic idea is that over the next few weeks, I'm going to be going over all of the telescopes, or various specific types. Because the thing to remember is that to an astronomer such as myself, everything, gamma rays to radio waves, it's all light. Optical telescopes refer to the light that our eyes can detect. So, when I speak of optical telescopes, we tend to call that light, but, it's all light. So with that in mind, how do optical telescopes work? Well, there are two types. Probably you've heard of these. There are refractors that use lenses to gather the light. In other words, the objective, the big thing at the front end of the telescope, or back end, as we'll discuss. In a refractor, it's a lens. In a reflector, it is a mirror. Now, it's a very specially curved mirror so that it can focus the light to a point. But we'll get into that. In fact, let's start getting into that now. So here are the light paths through the two types of telescopes. So the refractor uses a lens, a big lens as the objective, and focuses the light to a point, which then passes through that point a little bit into the eyepiece. And the eyepiece then turns the now diverging rays into parallel rays that your eye can then focus, and you can see the image. With a reflector, the light comes into a big tube, hits a mirror at the back end, and then is focused to the same type of point, or plane as the case may be. We'll discuss that in a minute for sure. So basically, those two types of telescopes use a different element to gather the light and then focus that light that's gathered into a point. Now, why do we use one over the other? Well, lenses are a bit expensive to make, and you can only make them so big before they actually sag under their own weight. Glass deforms. It can alter its shape. So a lens has to be very specifically curved, and it'll deform under its own weight after a certain size to the point that it's unusable. So they're also very expensive to make because of the precision needed. So we tend to use reflector. Now, there are more reasons for doing it. Lenses produce what's called chromatic aberration. In other words, the different colors of light are focused to different regions, different points, and therefore it blurs the color and other things like that. But mirrors have their own sets of issues. You've got to get them lined up just right because you need a secondary mirror to bounce the light off to the side. Otherwise, your big head has to be in the way of the telescope. So there's all these factors to consider, but generally speaking, you can make a bigger mirror. And the bigger the mirror, or the bigger the lens, the more light you can gather, because we're used to thinking of stars as being point sources. But it's actually a plane, a curved surface, but stars are so far away, it can be assumed to be a flat plane. And so the more of that you can gather, the more energy you've gathered, and therefore the fainter the object you can see, and the sharper the image, and things like that. So with that in mind, I mentioned the fact that your eye is actually not at the focal plane, where the light is focused. The eyepiece helps turn that focused image into parallel rays that your eye and brain can then focus and produce an image. But you can use a telescope, a refractor anyway, to project an image. And this is a setup we used right here in the center to project an image of the sun when Venus was going across it, a Venus transit as we term it. And that telescope in the middle is set up like it. So the sun didn't glare. We put a big black piece of poster board in the front end just behind the objective. And then we had one of our student assistants stand with a big piece of yellow projector card because we found it yellow did better than white to project the image of the sun onto. And so here's where we're actually projecting an image of the sun. You remove the eyepiece, and actually the big lens at the front end, the objective lens, will focus the light onto a plane and give you an image. So that's what's going on there. And as to what that image looks like, yes, it was a little cloudy that day, unfortunately, so we didn't get to see the full transit. But if you notice, you look real carefully, the clouds are just shadows. You can actually see details of the clouds if you shift the position of the cardboard, the poster board, so that the clouds are focused instead of the sun. A few days before, I'd done a test of this to make sure we knew what it was doing, because as you saw, we had a lot of people for the Venus transit. And I used a white sheet of paper, and there's a projection of the sun, and see how much detail you can get? And this is without an eyepiece. This is just the telescope, the big lens at the front end, projecting backwards and positioning that paper so it's at that focal plane, that place where the image will focus. So that's a brief, very brief rundown of how, optical telescopes work. And next week we'll get into some of the other telescopes like X-ray and radio and so forth. I hope you've enjoyed this. If you did, give us a thumbs up, give us a like. I know it ran a little longer than usual, but I think there's a lot of good information, and I can always talk more. So we'll do that again another time, though, if it's wanted, desired. So for now, though, you have a great day. Goodbye.